of the part which is about affine varieties. But we have missed several important points which we should somehow fix. So the first is, well, the proof of Hilbert-Nullstellensatz is bad. It's only over C with countable. So it doesn't, our proof, which we did, doesn't work for algebraic, for the field of algebraic closure of Q. So Nullstellensatz only over C. Another problem is that we did not prove existence of smooth points. And of course, this is part of commutative algebra, but it really has geometric meaning. And the third, we did not build the dimension theory. The idea about dimension theory that if you have a variety which has smooth points and irreducible, its dimension is the dimension of the set of smooth points. But then you need to prove something like if you have a variety of dimension d at subvariety should have dimension less than d. And for all of these things, there is a solution which is called Noether lemma. It says more or less the following, that if you have a normal variety, so X is normal, then X is isomorphic to integral closure of isomorphic to integral closure of just you take y, which is C of x1 dot xn, and then you take, and let's at t, and you take a quotient by a polynomial p of t is equal 0, where p of t is a polynomial p of t belongs to C, for instance, of x1 dot xn. So in other words, you have, so if you have x and and you have also projection from y to y is projected to a spectrum of x1 of polynomial C of x1 dot xn. Just you forget one coordinate. I mean, every time you have, you can think of that as forgetful map, or you can think of that as a map corresponding to embedding of rings, because this ring is embedded to this ring. Because there's a polynomial of t, so there is no relations between xi. So this gives you an embedding, and this map. So what's the preimage of a point? It's a set if you have a point with coordinates a1 dot an. Its preimage is a set of solutions P you evaluate P of A1 dot AN of T is equal to 0. So P now is polynomial of just one variable T if you evaluate it there. It has finally many solutions, generally speaking. If this polynomial is, we can also assume here that it's monic polynomial, so it has really precisely n solutions. Well, you have to take care, but generally this is true. For general point, this is true. So this means that up to some birational manipulations, every algebraic variety is what is called ramified cover. In the following sense, maybe if you have done things like complex analysis, Riemann surface, you know this, that if you have things like a function, say x goes to square root of x on C, this is not well defined. It is defined only locally. And it was Riemann who noticed that, and then he decided that you should just consider what is called Riemann surface of this function. Namely, you have locally branches, and then you glue these branches so that it will be globally defined. And then it's for this particular function, the Riemann surface of this function f is just a graph of so you have x goes to y equals square root of x, so it's y square is equal x. So like it's it has, if you look at this curve from this side, you will see that for each x you have precisely 2y, well except x equals 0, precisely 2y which are given by that, but locally every branch, I mean square root is locally well defined and continuous and analytic. And this happens for any polynomial equation. If you have x goes to root of p of x equals 0, well, xt. So you have polynomial equation on T, which coefficients of this equation depend on x polynomially. It's not hard to see that if you modify coefficients of your polynomials, very small, and all roots are different, the roots depend continuously and even analytically on your coefficients. So this function is locally well defined, and globally, if you want, you can try to glue its branches like one does with the square root of x, the same Riemann's construction. So what happens is you modify your x, your coefficients of our polynomial change, and then the roots also change smoothly. And as long as they stay different, they stay distinct, it's actually well defined. So your dependence of roots upon x, if there are precisely n roots and they're all distinct, you can move. It's not hard to see geometrically, and you can prove it using simple topology. But of course, since at some point some roots join together, like with this, around 0, around these points, this is not well defined. So it's called ramifications. If you have such a function, it's called ramified cover, and ramification points are points where your roots are allowed to join, and then in that points this doesn't make much sense because like square root around 0, it's not well defined. Okay, so this is the purpose of like this lecture and the next lecture. So let me remind you what we had last time. We defined dominant morphisms. F from X to Y is dominant if f of X is not contained in proper algebraic subvarieties of Y, or if it's not, I mean, if it's irreducible, this is like that. Otherwise, you have to check for each components. So it's proper algebraic subvarieties of X or its components. And then we don't consider components, irreducible components, proper subvarieties. This is dominant maps, and the important thing that with this something we proved last time. So claim F is dominant if and only if F star, which is a map from OY, from the ring of polynomial functions on Y, to OX, has no kernel. Should I explain this? So who remembers this well enough? Who doesn't remember? Well, should I? Okay, so let's do it, because I think you cannot reply either this or probably don't know. At least too timid to answer. So suppose it has zeros. So if A sits in a kernel of F star, this means that A is a function, and A applied restricted to F of X is equal to 0. This is because well, yeah, this is because you F star of A at some point, like X small, is the same as F as A F of this point. This by definition. So if A sits in the kernel, this means that F of X belongs, then F of X, or of X big, belongs to the algebraic variety, which is determined by function A. So one direction is clear, and the opposite direction is similar. If you have F of X belongs to some Z, which is a proper subset in Y, then you have, I'm assuming everything is irreducible just to shorten the proof. It doesn't matter. Just check for any component. Okay, if this is true, then there exists A inside OY, which vanishes. A restricted to Z is equal to 0. This is by definition of algebraic variety. Algebraic variety, proper one, is determined by some ideal. It's proper, so there is non-zero element. And then A restricted to F of Z is equal to 0, and the same argument implies that you pull it back to X and it becomes 0. Okay, this was dominant maps.
I want to ask a question about the image of a dominant map. Is it necessarily open? I mean, is it complement of?
No. So what can happen is, let me give you an example. So you can have C without C squared without 0. Yeah. C squared without 0, well, without divisor, X equals 0. This is image of dominant map, you go from spectrum of x of polynomials, C of x, y, t, and then tx is equal 1. So this is, the spectrum of this is just c squared without x equal 0, because you invert x. This is just, you add a fraction, 1 over x. And this is projected to C of x, to spectrum of C of xy, which is just c squared. You forget about t. Okay, then the image is open, but then you can take union of this and a line, like a line y equals 0. And this will still be a dominant map.
And its image will be?
Its image will be c squared without a line, and then plus the point y equals 0, x equals 0. Because this is the image of this line is just y equals 0, x is everything. This is one of the examples, and it is not reusable. You can do the same with the reusable. It's an exercise for you. I cannot improvise it, but it's doable. You just somehow invert more things and slightly. So what we can prove is that the image is what is called constructible map. So it's a constructible subset. Constructible subset is a complement of Zariski closed to Zariski closed. And any constructible subset can be obtained, if it is dense, can be obtained as image. Yeah. So we have discussed that some bit, and so the important thing that the dominance of morphism is interpreted as injectivity of the corresponding ring homomorphism. Okay, ring of fractions. We have discussed that a lot. So who doesn't remember what is ring of fractions? Who does remember? Who does? It's okay. Good. So what will happen now is that if you have x goes to y dominant, then OY is embedded in OX, and if they are all also reducible, X, Y irreducible, this gives you that the corresponding K of Y is mapped to K of X. This is rings of K of Y, K of X, rings of fields of fractions. So for each ring, you can just take all fractions with the denominator and well, with x over y, where a over b, where a and b are in this ring, and this gives you a field, and you have an embedding for each dominant map. This is important, and this would be used. You have to be automatic with it without thinking, because it's used every time. And then definition, f from x to y is birational if the corresponding map k of y to k of x is an isomorphism. So this means that rational functions are the same. This is why it is birational. And what we proved, I'm not going to use it, but it is very good for understanding of geometry. Maybe it's in the next slide, I don't remember. No, it's not. So if you have x to y, birational. You have here a divisor D. Here you have divisor f minus 1 of D. Divisor is a variety given by an equation. Once we have theory of dimensions, you can just define divisor as a variety of dimension 1. Okay, and then you have an isomorphism of the complements. You remove here f minus 1 of D, you remove here D, and this would be an isomorphism outside of D. This is clearly, since the field of fractions on X without D is the same as field of fractions on X. This is clearly implies this statement that it is an isomorphism outside of divisors implies that they are birational, but the converse is also true. And to find this, you just you consider this map, you consider the inverse map. Inverse map is defined only on the level of field of fractions, but then you just take all denominators of all the coefficients of your map and remove where they are 0. Then these denominators become invertible. Okay, now what we have is next is integral dependence. So element X in, so if we have A contained in B and X inside B small inside B big, or X inside B big is integral. If you take now the subring generated by this X and you want it to be finite generated as a model. And we proved last time, and I think this by now it should be pretty obvious, that this is equivalent to existence of monic polynomial. Monic means that it's leading coefficient is 1. Monic polynomial P of t in the ring of polynomials on A, such that P of x is equal 0. This is, then you can express each power starting from n, where n is degree of this polynomial, through the smaller degree powers, and this gives you finite generatedness of this ring. Should I explain that in more detail? Because it was last time, and okay.
Are the rings supposed to be integral domains?
Whatever is integral domain, I don't remember. Yeah, there's always, no zero divisors. Yeah, it's, well, here it's not used in state, but we shall always apply that only to the integral domains. Another important thing is that if you have two x and y, two elements which are integral, they generate something which is integral, and the reason is that if x and y are integral, you have the ring A of x, which is finite A model. Then you have A of x y, which is finite A of x model. Then you have like, this is like you have two fields, one bigger than another, but each finite dimensional over the next one. Then the big one is finite dimensional of the smallest one, and you just pick the bases. You pick the bases, you pick finitely main generators in this over that, in this over that, and then you multiply them. There is another way of doing it, which this actually uses noetherianity. And I proved that for noetherian. But in fact, if you know about symmetric polynomials, do you know about symmetric polynomials? Who knows about symmetric polynomials? Okay, then you can prove that without, because So there is an alternative argument to what I told you last time. So suppose you have x and y, x root of p of t equals 0, y root of q of t equals 0, then you can consider, like formally consider p of t as a product of t minus xi, and q of t as a product of t minus yi. This would make sense if you have a field and you can add algebraic closure, but if you don't have a field, if you have a ring with, well, you still can do that like on the formal level. But let's assume we work in a field, and I mean we have no zero divisors. Then you have the following new polynomial r of t, which is a product of t minus xi minus yi. So the coefficients of this polynomial are symmetric polynomials on xi. Coefficients of this symmetric means that they are independent on all permutations on xi and yi. So coefficients of this guy are polynomials which are symmetric on all permutations. So I have here j. It's a product of all I and j. This will be symmetric under all permutations of xi and yj. This is a symmetric polynomial on xi and yj, and we know that symmetric polynomials are expressed through elementary symmetric polynomials, and elementary symmetric polynomials are precisely coefficients of p and q. So this polynomial has coefficients which are polynomials of coefficients of p and q, so they belong to A. And then it is a monic polynomial which has x plus y as one of its roots. So this is how you can obtain a polynomial for which, like explicitly obtain a polynomial for which x plus y is a root. This is what you can do instead of using this step-by-step argument and arguing that you have an Noetherian ring, then sub-model is always finally generated. Have any questions, comments? Okay. Yeah. Now we can do integral closures. So if you have, you can do that either in just field of fractions of your ring, or you have two rings, B containing A, and you have K of B containing K of A, and we assume that it is finite extension. Then you take integral closure, so it's a definition, integral closure of A in K of B is all integral over A elements in K of B. So we know that each element of K of B, because it's a finite extension, is a root of a polynomial with coefficients in K of A. In fact, you can always multiply by denominators of all coefficients, and it will be a polynomial in A. But it won't be monic. So you take only elements of this field of fractions, which are roots of monic polynomials, and that's a ring, as we just discussed. This is algebraic integral closure. And of course, you can do that with A equal B. Just then you take all all roots of monic polynomials with coefficients in A. And as we had an example, actually, you have a ring where generated C of xy quotient by x squared is y power third. And then you can take T, which is equal to x over y. Then T squared is y, and T cube is x. So you see, this is a root of a monic polynomial, T, but it belongs to a field of fractions. This implies that this ring is not integrally closed in its own ring of fractions. Am I clear? So you can easily check that if you take the square of this guy, so T squared is x squared over y third over y squared, but x squared, so it's x squared is y third, so it's y third over y squared, it's y, right? And the same you can do with T cube. Completely, T cube is equal to x third quotient by y third. Y third is x squared, so this is x third over y over x2. This is x. So this is truly non-integrally closed ring. Another example of rings which are not integrally closed, and this is an exercise for you because I don't think I will have time to do it, is the ring Z of square root of -3. This is not integrally closed. And this exercise for you.
Corresponding to the fact geometrically that the corresponding variety has a singularity.
Here, yes, but here, of course, no. This corresponds geometrically to the fact that if you have this lattice, it's not Euclidean, but if you do this, well, it corresponds to something. I can't express this shortly, but you are invited to think about this. Okay, yeah, and what is normal? Of course, normal is when it's integrally closed. So definition, x is normal. Let's suppose that x is irreducible if OX is integrally closed. If you have several irreducible components, you have to also assume that it is true for each of them, and they don't intersect. Questions, comments? Okay, so important example, of course, is factorial rings. This is an example of integrally closed rings. It's much stronger, in fact, condition. So definition, R has prime decomposition. Oh, so X inside R is prime if the corresponding principal ideal is prime. Yeah. This means that, well, let's better say that for all. I mean, I think this is, yeah. Okay, here's the same definition. I'm not sure it's good one because maybe there's alternative which is probably non-equivalent. So for each xy equal P, X, or Y are invertible in your ring R. Anyway, R has prime decomposition if each element X in R is expressed as is the product of primes. I think yesterday you had, did you have yesterday the exercises for like prove that this ring has prime decomposition, that ring has prime decomposition? Anyway, now definition, R is factorial if this is unique. Of course, unique up to multiplying by invertible, exchanging of factors, like reordering, and so on. And of course, we know that Z is factorial. And today we have seen that polynomials are factorial, Gauss numbers are factorial. And yeah, so the statement, it's an easy result. Is it proposition? Proposition that if R is factorial, then it is integrally closed. And the proof is really simple. So proof. So consider a fraction. So you have t is equal u over y over v, such that is it v over u or u over v here? Yeah, u over v. Such that t is a root of monic polynomial. And we can assume that they have no common prime factors, because if they do, we just remove them. So coprime, u, v are coprime. Coprime means they don't have any prime factors in common. Then you have sum. You can multiply it by v power power n, where n is of monic polynomial of degree. Let's write it. P of t is equal to t power n plus a n minus 1 t power n minus 1 plus and so on plus a n, a0. Okay, in that case, we have that sum. Now we multiply it by v power n, we obtain u power, so it will be like u power power n plus v u power n minus 1 a n minus 1 plus v square u n minus 2 a n minus 2 plus and so on. Yeah, I just multiplied this. I plugged in u power v and multiplied by v power n plus dot 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 plus a0 v power n is equal to 0. Okay, and this implies that u power n divides v, which is a contradiction. It can't happen because they don't have any common prime factors. So this can happen only if v is invertible. V is invertible. And in that case, of course, our u quotient by v, I mean u over v belongs to our ring. So it's really integrally closed. Questions, comments? Good. Okay, so who already remembers well the proof of Gauss' lemma? And who have heard the proof? Well, I will be brief because most people apparently heard at least a bit of it. So Gauss' lemma is a statement about factoriality of polynomial rings. Mostly you use it to prove that the usual ring of polynomials is factorial, but in fact it's easier to prove it that theorem, Gauss' lemma, that if R, the ring R is factorial, then R of T is factorial. And the proof is not hard, so it takes a couple of lemmas and then it's immediate. So definition, polynomial P of T inside R of T is primitive. I remind you that this is a factorial, so greatest common divisor makes sense. So if greatest common divisors of coefficients of P is equal 1. So this means that this polynomial is not divisible but by any non-invertible element in P, in R. And then the point is that the product of primitive is primitive. So lemma 1, product of primitive is primitive. Proof, it's essentially y line. So suppose that P1, P2 is divisible by A, where A belongs to R, non-invertible. Okay, then R has some prime divisor, right? So then P of T, P1 of T times P2 of T is equal 0 modulo P, where P is prime divisor of A. Okay, then if you, this is polynomials now over a ring without zero divisors, because modulo P is prime, and any ring without zero divisors embedded into a field, and on a field this can't happen. Product of two non-zero polynomials on a field is never zero. It's an easy, I think here it's even written maybe. No, it's not, but it is easy. Just take the first non-zero coefficient of P, first non-zero coefficient of P1 of P2 and multiply them, and it will be the first non-zero coefficient of the product. Okay. And the second lemma is that irreducibility. So if something is irreducible over the field of fractions, it is irreducible. It is irreducible in R of T. So, sorry, converse. If it is irreducible in R of T, it is irreducible in a ring of fractions. So lemma 2, P irreducible in R of T. This, of course, weaker than P of T. P of T irreducible in K of T, where K is a ring of fractions of the field of fractions of the ring R. So proof, okay, suppose it is reducible, then you have P is equal P1, P2 in K of t. So suppose it's true. We can again multiply by denominators and obtain that, is it RP? RP is SP1 times S1 P1, S2 P2. And then we'll just remove all common denominators. We want R to be, so S1, S2 coprime with R and P1, P2 now, because they were originally in here, but we can assume there that SI, PI belongs to R. Well, PI belongs to R of t. We just multiply by all denominators, obtaining integer coefficients from R. Okay, so now this P1, P2 divides R. They are not primitive. But if they are not primitive, we can just remove all common factors and put them here. So these two guys can be assumed to be primitive. And then if this equation holds, this means that R is invertible. Otherwise, the product won't be primitive. OK. And now we can easily prove the Gauss lemma. So suppose you have you can take a prime decomposition in so you have P is product of Pi of t in K of t. Good. Well, I would assume so there is actually an easier way of doing uniqueness of prime decomposition is that okay, you take this, well, suppose you have this decomposition in R of t. It's an irreducible decomposition, but then they are irreducible in K of t, and in K of t the decomposition is unique. So this means that it is unique in R of t up to some factors which come from R, but in R is also unique. So if you have some polynomial, you can obtain it as a product of polynomials which are irreducible in R of t and elements which are from R, and then uniqueness is first you check that the irreducible factors in K of t are unique. This is because of uniqueness of polynomial decompositions in fields. And then for the constant factors, you use that R is factorial. Okay. Yeah, so you have an example then, namely a affine space, which is like C1 is spec of polynomial ring, and this is factorial by Gauss lemma, and this means that Cn is normal. And of course, every time you have some other ring with which is with factorial regular functions, then if you have X a spectrum of R factorial, then Rx times Cn. This is the same as we have discussed that. If you take a product of something with Cn, this is the same. The corresponding ring is just polynomial ring. So this will be spectrum of R of x1 dot xn. This is because, if you remember, this is something we already had, that if you have x times x is spectrum of A, y is spectrum of B, so this is regular functions on S, this regular functions on Y, then x times y is spectrum of A times B. This means that x times Cn is spectrum of A times over C with polynomials. And this tensor product is the same as, so A times polynomials by definition. Well, it's not by definition, but we have discussed that. You just build a correspondence between this, just a map to A of x1 dot xn, the standard map, and you check that it is isomorphism because using the definition of tensor product. Okay, so this is an isomorphism, then this is, you use that and you obtain this. Okay, so this gives you lots of, if you have some factorial rings, this immediately gives you lots of normal varieties. Comments, questions? Okay. I think we can have a small break now. And when we go back, I will tell you what I didn't tell you yet, that, okay, we have some normal varieties, but what can we say about integral closure? What we want to show that integral closure is, in fact, also a ring of functions on some variety. For that, you need that to be finely generated. This is what I'm going to show. So that integral closure is finely generated. It's not entirely obvious. In fact, it's not true in general, like without notoriety. So you need something. Okay, we're back. Now it's, according to it's 14:29, and let's go back at 13:34. And if you have questions, please ask. Yes, and also you have handouts. So we shall use it mostly for varieties, but in fact it's true for, in more general situation, it's true for any Noetherian rings, so theorem. You have A integrally closed Noetherian ring. And then you have finite extension B. Well, B is a ring containing A, and K of B over K of A is finite extension. And then yeah, find extension, and then you can B is integral closure. If it's not integral closure, just replace it by integral closure of A in K of B. So what you do, you start with a normal, say, variety. You take some ring extension, which just corresponds to taking like a polynomial. Well, we shall discuss that. Anyway, you take a find extension, and you take integral closure, and then B is finally generated as a model. In particular, from that it follows that B is finally generated as a ring, if it's A is finally generated as a ring. So this sort of takes care about normalization, but not quite. Well, we shall discuss this. Anyway, let's prove this result first. So proof. Step 1. So for step 1, we consider trace. It was something we have discussed a lot already. So you have A inside, B inside the B big, and you consider B like multiplication by B. It's a map from B to B, A linear. And you can consider, we denote trace of B, of element B, it's the trace of LB restricted to KB. And this trace is taken over K of A. So we consider K of B as a fine-dimensional space. And this would be an automorphism of this fine-dimensional space. And we take trace of this map in this fine-dimensional space. And the first observation is that coefficients, well, this is a root of monic polynomial. Yeah, everything is over C or over characteristic 0. Or let's assume everything A is a ring over C. So it contains C. Otherwise, now we shall have to take derivative, and we shall have problem unless the leading term is invertible. Anyway, so I claim that then trace of B belongs to A for each B inside the B big, because trace of B is, well, what is trace? Trace is derivative of determinant evaluated at 0, right? So it's, you take trace, determinant of I of T identity minus LB prime. You take d by dt and evaluate it at t equals 0. Okay, but this determinant is our friend. It's a monic polynomial with coefficients. No, we don't need characteristic 0. It's fine. It's a monic polynomial because it's an integer element. So you can be defined by a matrix which has integral coefficients in A. And anyway, this is monic with coefficients in A. So if you take derivative, you obtain something with coefficients in A. Okay. As a yeah, this is probably the best way of doing it. Now, also we have to notice that this bilinear symmetric form associated with trace is non-degenerate. So step 2. You have trace of x, x minus 1 is non-zero. And here we definitely use a characteristic of our base field as non-zero. Yeah. So you have to assume this. Precisely, thanks. No, characteristic polynomial can't be 0. Its derivative can be 0.
Derivative can be 0.
But then it's 0. It's fine. 0 is in B. So characteristic polynomial can be 0 because it has a root.
Yeah.
And its derivative can be 0. In that case, trace is 0. So for non-separable extensions, trace is 0. That's all. But 0, it's not a contradiction. But for characteristic 0, this is because this is equal to dimension of k of b over k of a. So this is non-zero. And then you have a bilinear symmetric form. Bilinear symmetric form. xy goes to trace of xy. Non-degenerate. It's a non-degenerate form on k of b. Okay. Step 3. I will choose a basis in B. So I choose a basis E1 dot En in k of B over k of A. Okay, all these guys are, I mean, yeah, they are. This is a finite extension, and I want to tell you that they can be. You can assume that they can be chosen inside, in fact, inside B. So I start with the base, but then now I will modify these guys to have them in B. So again, I take the minimal polynomial of each EI, and so I minimal or characteristic polynomial. Better to stay with minimal polynomial. So you write them like that. It's a so minimal. So EI is a root of polynomial A big I t power n I is equal to sum Aij t power j. This is the leading term, and these are smaller terms. So this is I is fixed, and j is less than ni. Okay, now I will make them into monic polynomials by dividing EI, multiplying EI AI. So this product, EI AI, is a root of t power ni is equal to sum j less than ni Aij AI power power ni minus j, I think, t j. Right? So I just multiplied ei. Ei was root of this. Then this product, it will be a root of that. You just, I mean, you rescale everything by ei. So this is monic. And then belongs, then this guy, the product. Sorry. B. So ei times ai belongs to B. Because there are roots of monic polynomials with coefficients in. So this is already, everything here is an A. We just took coefficients in the field of fractions and multiplied by all denominators, obtaining a polynomial with coefficients in A. Then we made this polynomial into monic polynomial and obtained that its roots belong to B. Okay. So we can assume, in the end of the day, we can assume that ei, e1 dot 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 en is a basis in K of B over K of A, and all ei belong to B. Now we shall take dual basis using the trace form. So the point is that, so let's denote I dual. It's again elements in K of B, such that this is a dual basis, so trace of ei, ej dual is equal to delta ij. So trace of ei dual is equal to 1, and trace of ej dual for different I not equal to j is equal to 0. This you can do because for each, I mean, you have two spaces, space and its dual. Duality is provided by our trace, which is non-zero. So it's a linear algebra. Every time you have a basis in the same vector space, you have a dual basis. It was step 2 here. So it's just dimension of the big field is a trace of 1, and then we did it a lot already because we applied that to the anyway. So let's now consider the it will be step 4 now. So step 4. I take M, which is a space generated by a submodel generated by E1 dual dot 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 En dual inside K of B over A. So it's A submodel. Okay, the important thing about that the submodel can be characterized. So M is a set of all vectors x in K of B such that trace of x multiplied by ei sits inside of A. This is because, let me explain why it is so. This is because if x sits in K of B, x is equal to sum EI dual, and then I multiply it by trace x and EI. This is the definition of the dual basis. So this, in particular, yeah, but since we are interested in guys where M is where these coefficients belong to A. So this is precisely how M is determined. And then this now we have this step 2 on the previous slide, which says that if you have some guys taken in B, no, step 3, no, step 1. Yeah, the trace belongs to A. If element, trace of something which sits in B belongs to A. So then, step 5, M contains B. This is because any element in B, if you apply trace, EI also belongs to B, the product belongs to B, and trace belongs to A. So this characterization implies that M contains B. But M is finally generated. A model, A not N, then a B also finitely generated. Good. There is some corollary which is wrong. Unfortunately, I apologize for that. It's my oversight. Yeah, so this is, if you look at our statement assumes from the beginning that B belongs to an extension of a ring which extension of a field of fractions of a ring which is integrally closed. So in fact, we didn't prove yet. It would have been after Noether lemma. I told you about Noether lemma in the beginning, that normalization is finally generated. So far, I don't think we have it. I'm sorry about this. This is finally generated as a model. It's finally generated as a model if A is. However, what we just discussed is that Noether lemma, this is something I told you in the beginning, and I will prove Noether lemma in a couple of lectures, that every variety can be obtained as ramified cover over Cn. This is X. Well, every variety has a normalization which is obtained as ramified cover. Means has a finite, but this ramified cover is satisfies assumptions of our theorem. So this statement is still true, but up to Noether lemma. I'm sorry about this. So I promise to tell you in the future that corollary. So far, it's not proven. Sorry about this. I will remove it. That if you have X variety, a spectrum of A finitely generated, and A hat is integral closure of A, then A hat is finitely generated. but it has the following, it's not proven. However, what we proved, and this is truly proven, that this is really corollary from the statement above. Suppose that X to Cn are a morphism of algebraic varieties, and K of X is a finite extension of K of Cn. K of Cn is a ring, the field of rational functions. So it's dominant morphism. Then integral closure of OX is finitely generated. And I promise to you that I will construct such a map like very soon. So this allows us to define, so far it will work only for such varieties, but then it will work for all varieties. So definition, suppose that X is a affine variety, and A hat, A is the ring of regular functions on X, and A hat is integral closure. And then if A hat is finitely generated, you can, every finitely generated variety is a variety of, every finitely generated ring is a ring of functions of some algebraic varieties. So A hat has spectrum, which is algebraic variety, affine variety, called normalization of A, of X. It's funny, because somehow it shouldn't be hard. We already know that you add the integral closure is something where you have add finite elements. It shouldn't be hard to show that when you add all finite elements, you will obtain something which is finite over your ring. But in fact, you see it's tricky, and even I made this error. So you shouldn't do it. Geometric meaning. It's opposite. So if you have, because it's the ring of functions on X is embedded into ring of functions of its integral closure. So you have A hat, which is normalization. It maps to X, and it's dominant, it's birational, and finite.
And X hat is a ramified coupling of a finite.
Well, ramified in very strange sense, because in fact there's no ramification, it's generally one-to-one. It is, but if you think like geometrically, it's not ramified. It's one-to-one. So for each variety, you have another variety. It's called its normalization. It's integrally closed, with integrally closed ring of functions. But so far, we proved it only under this additional assumption, where you have a dominant map to Cn. Well, you can always have a dominant map to Cn, just project it to C1 or to C0. It's not hard, but this is tricky. Okay. I think I'm out of time. So if anyone didn't take the handouts, you can have it. This is for the discussion in next Thursday. Yeah.